All right, well, tonight we want to talk about center of mass. Centroid. Of a plane region. So its applications. Really not any new math, it's just new formulas, new ways of seeing how calculus actually derives some things. And it starts with this, a lamina is a thin plate, thin flat object, so thin enough, so thin that it can be modeled as a plane region, a two-dimensional object. And we can do some things for balancing and for forces on these kind of things by the following consideration. In one dimension, we can calculate the center of mass as just the mean point of mass. And by the way, the book is going to call this the center of gravity. I'm going to call it center of mass just to be picky, because what we're going to do is consider masses like this: M1, M2, M3, M4, a bunch of masses placed, say, along a line. And suppose I have this line here is weightless, and so this mass here pushes down at point x1. This point mass here pushes down at point x2. This pushes down at x3, and this pushes down at x4. There's some point where I could put this and balance it, right? And what it turns out to be in physics is the mean mass point. And so if you consider this the x-axis, and these are points along the x-axis, it's m1x1 plus m2x2 plus m3x3 plus m4x4, all divided by the sum of the masses, m1 plus m2 plus m3 plus m4. There's a more calculus way to write that, of course, right? You could write it in sigma notation, and you can say, oh, it's the sum, k equals, maybe I should put this in more general notation. For n masses, we could put plus dot 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 plus mnxn for n masses, and then same thing down here, plus dot 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 plus mn. So here's for n masses. We'd have 4 here in this example, but let's consider in general. This is the sum k equals 1 to n, the number of masses of mk xk over the sum of the masses, k equals 1 to n of mk. So this formula is the sigma notation for this, but they both calculate x bar, the mean point of mass. You ever taken a statistics class? You calculate the mean of a set of data. Sometimes you call it x bar. I wonder what it is. If you think about it, this is actually exactly what you compute in statistics for a frequency distribution. If position x1 curves with a frequency x1, well, it sort of does because there's m1 pounds at position x1, right? Well, let's not say pounds, let's say kilograms. Pounds is actually a force. So let's say mass kilograms 1 times position 1 plus kilograms 2. You have this frequency at point x2. And so these are like how many 1 pound weights, 1 kilogram masses are sitting at each of these 4 points. So it's like, and if you computed the mean, the mean of any set of data that had these frequencies, M1, M2, M3, M4, like, and you computed this and divided by this would be the average that we usually calculate, called the mean, right? For instance, if I have M1 students getting score X1, M2 students getting score X2, and so on, MN students getting score XN, I have these all together. This is just the sum of the scores, right? And then this one is the number of students, right? M1 students plus M2 students and this score plus, and so I'm adding together all the scores, dividing by the number of students. I'm computing the mean, the average, right? Sum of the scores, but that's what this is, except it's put in the frequency distribution. M1 got this score, M2 got this score, and so forth. So all this really is the mean, and we use the same notation as a statistician would. But see me using different fingers here. I've been washing my hands fervently with COVID going around, so they're getting real chapped. And this cold weather comes in and breaking all my fingers open, trying to draw out the board all day. All right, so sorry about that. I'm gonna fumble around a little bit on that. This then is the center of mass. It turns out also to be the balancing point. The plates here at X bar, where you can place a fulcrum and the weights would balance. Gravity would push equally on each side and balance out. So why don't we call it the center of gravity? The book does, because they're just being sloppy. I wrote them once and they never wrote back, or twice and they never wrote back, so I just gave up. It wasn't important. This is the center of gravity if you're in a uniform gravitational field, or essentially uniform, like you're sitting on the Earth. But if you're way up, far away from the Earth, and these masses are way far apart, so they experience this one has a different gravitational force than this one, and this one, and this one. Then this is just called the center of mass for the units. So I will call it that. The book will call it center of gravity. It doesn't matter. Whenever you're in a uniform gravitational field, do the same thing. But the point is, you can compute the mean point of mass there in 1 dimension, just like that. And so there's a problem on the homework, so it's similar to this example, just to motivate all this stuff. What we really want to work with is plates. What's the balancing point of a plane region, right? Instead of what's the balancing point of the set of discrete masses. But this is gonna lead into that. So suppose I have this example, a mass of 2 kilograms is at X equals -1. A mass of 4 kilograms is at X equals 0. A mass of 1 kilogram is at X equals 2. And a mass of 3 kilograms is at X equals 3. Just like this, right? If I just said this is -1, 0, 2, and 3, and these are the masses. Find the center of mass, the balancing point for this in a uniform gravitational field. The center of mass, there's a homework problem just like this, is simply that formula there. X bar equals, you take the first mass of 2 multiplied by the first position -1, plus the second mass of 4 times the second position of 0, plus the third mass is 1 multiplied by the position 2, plus fourth mass is 3 multiplied by the position 3, divided by the sum of the masses, right? 2 plus 4 plus 1 plus 3. And what do I get? Let's see, -2 plus nothing, plus 2 is 0, plus 3 times 3 is 9 on top. And on the bottom, I've got 4, 7, 9, 10, right? So the balancing position is X equals 9/10. That would be where this one plays. Easy enough, right? One physics problem, no calculus in it whatsoever. It's discrete masses, right? Now, we can apply this principle to find the x coordinate or the y coordinate by symmetry of the center of mass of the balancing point of a lamina, something that can be modeled as a plane region. With density rho delta, excuse me. Some books use delta, some books use rho. This book uses delta. All right. And how are we going to compute that? Well, we do what we do a lot of times in calculus. Here's your plane region. Suppose the plane region, call it R, goes from x equals A to x equals B. And we want to find what is the balancing point in the same way. We could think of partitioning the x-axis up like we always do, x0, x1, x2, all the way to xn for B. So into n subintervals, right? And then over each interval, we'll pick an intermediate point, x1 star in the first interval, x2 star in the second interval, and so forth. At each star point, we then make a rectangle that goes from the bottom curve of the region to the top curve, makes it that tall, and we make a rectangle of this width of the interval, which is delta x1, right? It's x1 minus x0. And then we do another one here at x2 star right here. We go from the bottom to the top, make another rectangle that high, and so on. And we fill this up with little rectangles, and we say, well, the balancing point of the plane region ought to be approximated by the balancing point of these rectangles, right? So the balancing point of the rectangles is a discrete problem. You can think of this as a mass 1, mass 2, mass 3, mass 4, mass n, right? A bunch of masses sitting at discrete points. Aha! So I can calculate the exact balancing point of those rectangles. The rectangles have, well, what's their mass? This is what a density function does. If you have something of uniform density, you just take the density times the area, and it gives you the mass for 2 dimensions. And 3 dimensions, it's density times the volume, or 1 dimension is density times the length. But in 2 dimensions, it's density times the area. So you take delta times the area of rectangle 1 plus delta, let's put this here. Let's say M1, that the mass of the first rectangle is the area of rectangle 1 times delta plus, and then M2, the second mass here, is the area of rectangle 2 times delta, and so forth. The mass of rectangle N, thinking of these as discrete masses, is AN delta, right? Where delta is the, I hate to do it this way. Really, delta can be a function of x, right? You can make something where the density varies as x changes. So think of these as being functions of x, but the book doesn't do any of their functions of x, so I'm just going to leave it a constant also. So for this section, we'll let delta, the density, be constant. But in practice, it can vary with x, and these formulas still, most of them hold. They're just trying to keep it not confusing by making it constant. And that's what most, materials made on Earth are anyway, mostly constant density. Right? You have to not mix them, be very careful they settle just right, and then maybe they don't come out uniform density. So that's what we have here. Those are the masses of the rectangle sitting on here, and their positions we can say are approximate positions. X1 star, X2 star, up to Xn star. All right, and so then what is their center of mass? Balancing point. Center of mass of the rectangles is what? Well, we take M1, X1 plus M2, X2, etc., all over the sum of the M's. We're going to take M1, which is A1. Actually, let's multiply this out here first. Let's say, what is A1 delta? A1 is the area of the first rectangle, so it's the height. If we call the top curve, I should call it the same as the book. Let me make sure you the same. Let's see. Yeah, they just called it f of x. They didn't call it anything more than that. So let's say that this height of the distance between the two curves is f of x1 star. And the height of the last rectangle is f of xn star. Right. Now then, area 1 is the height times the base, so it's f of x1 star, f of x1 star, the height, times the base, delta x1, right, the width of this one, plus all the way down to an x, and then times delta, I'm sorry. And the last one has mass f of xn star, delta xn, that's the area, height times base, times delta, the density. And so the area times the density gives you the mass of the last one. And so when we go to find the center of mass, I add up all these masses on the bottom, which is sum k equals 1 to n of the masses is f of xk star delta xk. This is capital delta times little delta, the density. This is lowercase delta, that's uppercase delta. Even though it's smaller. All right. That's the formula for the kth mass, right? Height times base times density gives you the mass of the kth, gives you the kth mass. I'm sorry, I'm making it hard to see. Now, what do we put on top? There we have to put each of these same masses, each multiplied by the position. So we'll put sum k equals 1 to n of the mass f of xk star delta xk little delta times the position xk star. So this is mass times position summed over masses summed. That gives the center of mass of the rectangles. Center of mass along the x-axis, as though you're trying to balance it with your finger right here, a whole bunch of little rectangle widths, right? That's where the center of mass would be. Now what happens if we want the balancing point of this curved lamina? How should we find that? I bet you can guess. In the limit as the number of rectangles goes to infinity, if this f of x is continuous, this limit will reach the same number, and this value is by letting n go to infinity. Since we'll get the same number as long as f is continuous, we'll call that the center of mass of the lamina, whose height of each xk star is f of xk star. If the center of mass of the lamina, denoted x bar, and it's the mean in statistics, and it's the limit as n goes to infinity, or the book right is the width of the partition goes to 0, norm of the position. the norm of the partition goes to 0. F of xk star let's write another order. I'm going to reorder this and call it sum k equals 1 to n. This is the top, just put the limit on it. Xk star, f of xk star, delta, capital delta xk. So that's just the top with the order interchange to the multiplication, and then take the limit. And then the bottom, I'll interchange the order and take the limit. I'll get limit n goes to infinity of the sum k equals 1 to n. Everything the same except no xk star in here. It's f of xk star delta xk. How about that? Oh, what a mess. How can we rewrite that? By definition of the definite integral, what is this? What is this? If I take the bottom first, right, the delta can come out as a constant, but in practice, it could be a function of xk star, so I'll leave it in there. If I take the limit of the sum of a function of xk star times delta xk, what is that defined to be? That's defined to be the definite integral of this function. You put in x for this and dx for this, and you get the integral from a to b, where the lamina runs on the x-axis, of this with xk star replaced by x times delta times dx. So you get this integral. You just integrate the density times the height of the function, the lamina, at each point, and that gives you the bottom. Because this is just the definition. I mean, if you wrote this, you just write integral f of x dx, right? That's the definition of integral f of x dx. If you put a delta in there, that's just a constant that's this in there. Now, the top is exactly the same thing, but you're integrating this function. You replace each xk star with x, and you get the same integral, except you've got x in front. X, f of x, delta dx. There is the formula for the x coordinate at which you can balance the center of mass in the x direction, as though this was a bunch of tiny masses getting smaller and smaller, and your finger gradually settles down to it's the same point no matter how you partition this up. It always comes to the same point. That's where it's going to balance. Okay. So there's the center of mass x coordinate of a plane region. Now, what about the y coordinate? We can do exactly the same thing of the y coordinate, provided we write the width of the lamina f of y. So we put y, f of y, delta dy, but we don't have a width function here. So if we want to write it in terms of a height function, f of x still, we have to do something else. So we'll say for the y coordinate of center of mass, or you can balance it in the y direction. Well, we'd have to consider the same picture. We're not going to write the height of the lamina as a function of y. We're going to the width of the lamina as a function of y. There's your plane region R. We're going to still break it up into little rectangles like this. How will I find the balancing point along y if the rectangles would make her like this? And it's the same setup as before. I just have to redraw this with a y coordinate. What you do is you say, well, this one has height f of x1 star still. You take some point in the first interval. You take some point in the first interval x1 star to get the height here. And then you can think of it as a mass or an area times delta, right? The area times the density gives you the mass. But the area is f of x1 star delta x1, or delta x1 is the width. Oops. And then suppose I want to consider its position as pushing on the y-axis, I have to take right in the center. So if I want to, so this would be the mass one, but if I want y1, that's halfway between here. So I'll say, oh boy, this one's gonna be a little harder, huh? This is not the way they wrote it in the book. I'm gonna have to simplify this region somewhat. I'm gonna have to do this. For the y coordinate of the center mass, we can only use this formula in the special case. That the bottom is y equals 0. The other one works regardless. So we give something like this, and we do the rectangle like this. For this now, we'll say that the center of mass, in order to get the same formula, is halfway up here. If this width here is f of x1 star, you take some point in the first interval and get the height of the first rectangle. Then where's its center? It's at 1/2 f of x1 star. Right? Halfway up the rectangle. So you can think of this as a single weight at halfway up, pushing down with all its mass. The mass one is height times width, that gives you area, times density. And the position is 1/2 f of x1 star. And so what you get now is y bar is the sum of the masses. M1 would be f of x1 star delta x1 little delta plus dot dot dot. Oh, I'm sorry. And then times the position. The position is 1/2 f of x1 star. And then you do that for each of the masses. You get plus height xn f of xn star times width delta xn times the density delta. That gives you the mass of the nth one. Multiply it by its middle position of the last rectangle, which is 1/2 the height of this one. 1 times 1/2 f of xn star. There we go. And so that will be the mass times position plus mass times position plus mass times position all added together. Then you divide them by the sum of the masses, which is f of x1 star delta x1 little delta, and leave this off, right? It's the same sum of the masses as when you added them up doing the vertical construction. So the bottom is the same. And what you get then, I better put it out here. This is for the rectangles. And so this is the center mass of the rectangles, and for the center mass of the lamina in the y direction, in other words, where you can put the fulcrum here, y bar, and balance it on your finger on this side, you have to take the limit as the number of rectangles goes to infinity, with the widest one going to 0 of the top, and also take the limit of the bottom. Right? So this is the approximation for the rectangles, and then in the limit, you get the same number. You call it the balancing point or center of mass in the y direction. Now, what does that add up to in the limit? Well, the bottom is the same, right? It's limit n goes to infinity, sum k equals 1 to n, f of x k star delta xk. I rearranged the order of multiplication. And on the top, limit, top is different though. Limit n goes to infinity, sum k equals 1 to n. 1/2 f times f is 1/2 f squared. One half f squared times little delta times delta xk. That's a little different than the formula for the x coordinate. The bottom one comes out to be the same integral, right? You're integrating this, but you're taking the limit of the sum of this. So what you're doing is the integral from a to b of this. F of x delta with xk star replaced by x. So by definition of definite integral, this means this. And by definition of a definite integral, you're integrating this. So the top one is the integral from a to b. 1/2 f of x squared delta dx. This, by definition, is this one. That's what the definite integral means. And this is the center of mass in the y direction. The point you can put your finger and balance the lamina if gravity pushed this way. Now, why is that also important? You now think of taking the lamina and turn it flat like that. Where does it balance in both directions? I want to let it tip any direction and balance it on my finger. There's a point right in here that we just computed. X bar, Y bar. Since it balances this direction and this direction, if you turn it flat, I can balance that plate on my finger at the point X bar, Y bar. So you need both those coordinates in order to find where it would balance if you turn it horizontally. So these are the two formulas. I'll say what you have to do is memorize these two for this section. These are the center of mass coordinates for a lamina. Part of that derivation takes so long, but actually it's important to understand what goes on. This is a mathematical modeling, what you do. So these are the center of mass coordinates where you could balance the plate on your finger if it had uniform density delta. And you can change delta to be a function of x and it still works. That's why we left it in the integral. Now, let's do this one. Here's the kind of problem you want to be able to do for your homework. Find the center of mass and the mass. I want to make this additional note. Note, in addition to this, the denominator of these we'll call it m, is the integral from a to b of f of x delta dx is defined to be or called the mass of the lamina. Why is that, can you think? Pretty easy, actually. What this is the limit of this, you take the sum of f of x k star delta x k is the area of the kth rectangle, that delta is the mass. This is the mass of the kth rectangle. Sum k equal 1 to n, so the sum is the mass of all the rectangles. We take the limit of some of the rectangles, that ought to be the mass of the region, right? So by the way we define it, where we've summed the masses of the rectangles and took the limit, as the number of rectangles goes to infinity, we wanted to find that to be the mass. And so we can also calculate the mass as well as the center of gravity. You want this formula too. Now the problem says, find A, the mass, and B, the center of mass, coordinates x bar, y bar, of the lamina, the plane region, with bounded by, and we'll stick to this case here that we did at the end, where the bottom curve will be y equals 0, and the top curve will be y equals f of x. I should have written that in. I said the height is f of x k star, but that means this is the curve y equals f of x. We'll stick to this case where the bottom is 0, so we can use both formulas, x bar and y bar, even though x bar works in either case. The lamina below y equals square root x of density delta equals 2. I don't think I specified the units in here. Let's say its density equals 2 kilograms per square meter. All right, and the idea is if you integrate kilograms per square meter over this thing, then you'll get the kilograms for it. Maybe I better move this back over here. How about that? I like to draw the picture because I think the understanding comes better when you actually see the picture. All right, here's what we have: y equals square root of x. Oh, I'm gonna put the endpoints. The endpoints were oh, and the line x equals 1. So this is below, and then the lamina below this for 0 less than or equal to x less than or equal to 1 of that. So here's the picture. It goes from 0 to 1. Here's the curve y equals square root x. I wonder what the mass of that is, and I wonder where I could turn it and put my finger and so it would balance, right? Well, the mass just has this formula. Mass, all you have to do, and it's very easy, is you integrate the height of the function times the density from A to B, right? That's the definition over there. So the height of the function is square root of x. The density is 2, we were given that. And we go from A to B, that's where the rectangles start. You're thinking of filling this up with rectangles, right? And x equals 1 is where the rectangles end, so you integrate from 0 to 1. Easy limits, right? So I remember that x square root of x can also be written as x to the 1/2, and thereby I can integrate it, right? Integral x to the p is x to the p plus 1, or 3/2, over p plus 1, 3/2. Right? And then it's all multiplied by 2. Plug in 0 and 1 and take the difference, right? So there's fundamental theorem of calculus to evaluate that integral. Write an antiderivative, evaluate the two endpoints, take the difference. Well, this actually comes out to be 4/3 x to the 3/2. Plug in 0 and 1 and take the difference. When you plug in 1, you get 4/3. When you plug in 0, you get 0. So this just comes out to be 4/3. 4/3 what? Well, we integrated in units of kilograms over the square area. This comes out to be kilograms. So it comes out to be 1.333 kilograms. Right? That seem all right so far? Now, I should move this a little more. Now, what about the center of mass? Well, we have another note. these two things here, this is called the moment of mass about x equals 0, and this is the moment of mass about y equals, about y equals 0. I won't write those down, but you calculate this moment divided by mass, you calculate this moment divided by mass, and that tells you the coordinates here. So for x bar, we need to calculate the top integral here. We've already calculated the bottom. Integral from 0 to, let's put it a to b, x, f of x, delta dx. And the nice thing is the top integral looks just like the bottom, except you stuck x in there, right? That's what we calculated to get the mass. We put x in there, now we can calculate the moment of mass. And so we write the same integral we did before, and that saves a little work. Integral from 0 to 1, square root of x times 2 dx. Well, we just stick an x in here. And then y bar is this one. We'll need this one. So that we need that for x bar, and then we need this one for y bar. Let's just erase it. Integral of 1/2 f of x squared times delta dx. A to b is the numerator of the y bar. Well, let's see, that's 1/2 integral. Now f of x is square root of x, f of x squared is x, right? And delta is 2. So this time we just have to integrate 2x. That gives us x squared, and it goes from 0 to 1 as the endpoints of the lamina still. So it's 1/2 x squared, plug in 0 and 1 and take the difference. This just comes out to be 1/2. And I should have finished this one. This one you write as x to the 3/2, right? Wait a minute. Yeah, x to the 3/2. And so what you have for this one was 2 integral from 0 to 1 of x to the 3/2 dx. Well, that's twice x to the 5/2 over 5/2 from 0 to 1, which is 4/5 x to the 5/2, plug in 0 and 1, or just 4/5. Plug in 1, you get 4/5, plug in 0, you get nothing. Their difference is 4/5. So here's the numerator of x bar, here's the denominator of x bar. Then x bar is the number we computed here, 4/5, over the mass that we found, which was 4/3. So the moment of mass in the x direction is 4/5. The mass of the object is 4/3. And y bar is the second integral we calculated, 1/2. That's the moment about y equals 0, divided by the mass, 4/3. And we just have to calculate top times bottom is 3 over middle times middle is 8. So we get 3/8. And then top times bottom here is 12 over 5 times 4 is 20. These 4's actually cancel, and what we get is 3/5. And so there we go. The coordinates of the center of mass is 3/5 for x, 0.6 about here, and 3/8 for y, a little less than half here. Look at these to see that they're right? Most of the mass is down at the bottom, so I know this ought to be less than here. So I know this ought to be less than 4/8, right? And it is. It needs to be somewhere in the region of less than 4/8. And over here, it ought to be most of the mass is to the right, so it ought to be the right of 1/2, and it is. And this is the balancing point then. X bar, y bar is 3/5, 3/8. Well, look, all right, that's what you want to do for your first homework in there. Let's move this one over then. Now, some of these are actually simpler than this. Symmetry can be used when your density function is a constant, which is what we're going to do for all the problems here, just because that's what the book does, and I want to have these things not made in the book. For example, suppose I gave you a picture that looks like this. I take a plane region that's a triangle, and this is the line y equals 1 minus x, and this is the line the graph of y equals 1 plus x. And then on the bottom, I get bounded by y equals 0, so the second formula applies, not just the first one. And this is our plane region. Now suppose delta equals 3. Find what is the mass of this one? Well, I'll give you a little hint that makes this a whole lot easier. If you want, you can just find the area, and since delta is a constant, you can just take the area times delta. So we use the formula we did, integral from a to b of f of x delta dx. But if we pull delta out, delta is equal to 3. We can say it's 3 times the integral from this is minus 1 and this is 1. Well, let's just say integral from minus 1 to 1 f of x dx, where f of x is the top curve. F of x is a piecewise defined function. It's equal to 1 plus x, or x less than 0. That's equal to 1 minus x for x greater than or equal to 0. Oh, what a mess. That's going to be a messy integration, but what can I do that's a lot easier? Yeah, that's easier, even easier than that. What is this? That's just the area of the plane region. That's the area of the triangle. All right, if you take the integral of f of x dx, it's just the area below the curve. So without breaking up into integrals and doing all this kind of thing, just use the fact that it's area below the curve and say, I know the area of a triangle is 1/2 base times height. The base is 2 and the height is 1, right? If you figure out the intersection point here. So it's 3 times the area, 1/2 base times height is 3 times 1/2 base times height. Oh, it's just 3. So the mass of this thing is 3 kilograms or whatever the units were. Just for science purposes, we won't use pounds, I started to say earlier. Pounds is a force. The unit, what you do is if you take kilograms and multiply by the acceleration of gravity, meters per second squared, then you get newtons. That's a force. Similarly, in English units, if you take slugs, that's a mass. Then you multiply by gravity, so many feet per second squared, then you get pounds. So pounds is the force, but slugs is actually the unit of mass in the English system. So we could say this is 3 slugs, or something like that. People don't use that term very often. All right, so there's the mass computed, not by doing a complicated integral, but just realizing, oh, it's a triangle, 1/2 base times height. When this is a constant, you can always pull it out like that and save yourself a lot of trouble with the integration, right? So that's the bottom of both the quotients to calculate x bar and y bar. How do I compute the numerator? Well, what's the numerator? Top of the quotient for computing x bar, which we also call the moment about x equals 0 of the mass, is what? What's the moment here? Well, what you do is you say, if this is in uniform gravity, and it is, if this has uniform density and uniform gravity, and it is, right, the density is constant, then I'll just be able to put my finger right in the middle about it, right? This triangle pushed this way is just the same as this one will push down on this side, just the same as this one pushes on this side. So you simply say is 0 by symmetry. In fact, you don't even have to calculate the top. You just say x bar equals 0 because it balances. I was just showing how to have your homework time. So I'll tell you what we did. We said, if you want to compute the mass of this nice triangle here, we can do the complicated integral f of x delta dx. If delta is a constant, though, you can pull it out and you get 3 times integral f of x. But what's integral f of x? That's the area under the curve, right? So it's the area of the triangle. You can take the density times the area of the triangle, 1/2 base times height, and calculate it without doing the integral. When delta is a constant, you just find the area times the density. So that's a nice shortcut. And then the other thing is, when density is a constant and you have a symmetry like this, you say, oh, I can see that it bounces right on my finger because this side is the same as this side, and they cancel each other out. That's exactly right. Don't calculate this complicated thing when there's symmetry. It just balances right in the middle, right? Which makes it really easy for a circle. What's the balancing point of a circle? A disk, I guess I should say. These Bourbaki and the famous mathematicians and so forth try and make clear distinctions to make their proofs rigorous. But a circle is actually the boundary, and the interior of the circle is the open disk, and the circle with the interior is called the closed disk, and they have those kind of terms. What's the balancing point of this closed disk? Right? Symmetry says it's the center, right? If this is a uniform density, then it will bounce right on the center. We all know that from experience. So you just say, oh, it's right at that center point. You don't have to do any integrations, right? All right, so that's what we'll do here on for x bar, unless we don't have symmetry in the y direction, right? If it was a diamond or something, then we could say, aha, symmetry this way too, right? But no, in this one we're going to have to calculate. So the top of the quotient for y bar, which we call the moment of mass in the y direction, about y equals 0. Is, well, we have to look at that integral. It was 1/2 integral from a to b. Let's put the 1/2 inside. Integral from a to b, 1/2 f of x squared delta dx. The book put the 1/2 inside, so I'll just copy it. But you put a constant in and out all you want, right? So what is that? Now we have a trickier integral. This is the integral from -1 to 1 of 1/2 f of x squared, but f of x changes. It's defined to be 1 plus x on the one side, 1 minus x on the other. And delta is 3. It's over. So what we do when the definition is broken into 2 pieces, we just break this into 2 pieces. We'll say this is, well, let's write it one more time. It's 3/2 the integral from -1 to 1 of f of x squared dx, right? Let's pull the constant out. And now I'll say this is 3/2 times, and you break this up, integral from -1 to 0 of f of x squared dx plus integral from 0 to 1 of f of x squared dx, right? Remember that formula for calculus 1, integral from a to c is integral from a to b plus integral from b to c. Right, it was this idea that if you're taking the area of the curve from a to b, you can take the area from a to c and then from c to b and add them, you ought to get the same thing, right? As a concept. And you can prove that that was actually true. So I'll break this up into the sum of these 2 integrals, and now I can do this, right? Because this is 3/2 an integral from -1 to 0. On the interval from -1 to 0, f of x is equal to 1 plus x. All right? And on the interval from 0 to 1, f of x is equal to 1 minus x. So now I can compute this, break it up into two pieces. Now it is possible at this point to recognize that you're going to get the same moment of mass from the same. So actually you can put 2 times 1 of these, but we'll proceed naively here, which would then allow us to apply this to more general reasons, right? But we'll just to integrate this, we'll multiply it out, right? This is integral of x squared plus 2x plus 1 on -1 to 1, but it's the integral of x squared minus 2x plus 1 on the latter interval. There it is. Just getting this on and open. All right. This is where it's time to tell a joke, probably wake everybody up. Anybody's aspiring comic, maybe Heidi's part-time, I don't know. Here's this one. X cubed over 3 is the integral of x squared. Integral of 2x is x squared. Integral of 1 is x. Right? And we need to plug in this at 0 minus 1 and take the difference. And this one here is x cubed over 3 minus x squared plus x. Plug in 0 and 1 and take the difference. Now these have names, this top, these moments of mass. Maybe I should move this back just for a second. The moment of mass about y equals 0 is the moment, y equals 0 is the x-axis, right? So we'll call it the moment about the x-axis, and we'll write this as mx. Right? Kind of strange. We find the moment along the y-axis and we call it mx because it means it's the moment about the x-axis. Similarly here, we can call this one my, the moment about the line y x equals 0 because it's the y-axis. So the moment in the x direction is my, the moment in the y direction is mx because it means the moment about the x-axis. So I'll give it those letters, and now we're calculating mx here. Put this back. Let's see. So this is the top of the integral for y bar. Been so long we probably forgot, right? This is 3/2. And let's see. If I plug in 0, I get nothing. And then I plug in -1, and I subtract the bottom. And when I plug in -1, I get -1/3 plus 1 -1. So that's plugging -1 in, and I subtract that, and the top one is 0, and then I subtract the bottom here. All right, so that's the first integral, and then plus the second integral. I plug in the top point 1, and I get 1/3 -1 plus 1, plugging in x equals 1, and I subtract from that when I plug in 0, which is 0. So we've got that, lots of parentheses. Top integral, top endpoint minus bottom endpoint. The second integral, top point minus bottom point. What does this add up to be? It's 3/2 times, let's see, these cancel. I got -1/3 is 1/3 from this one. And then these cancel, wait a minute. I didn't write this right. This is +1, right? -1/3, oh no, it's -1 in there. All right, okay. And so these cancel, yeah. And so we've got a third here, and then we've got a third here. 3/2 times 2/3, it just comes out to have unit moment of mass in the y direction. So we have calculated my, the moment along the x-axis, is 0 by symmetry. The moment along y-axis, and the moment along the y-axis, meaning the moment along y, meaning about the x-axis, we just computed as 1 by integration. We have the mass came out to be 3 because it was a triangle of unit area and you had density 3, so it's just 1 times 3 is 3. So the balancing point, x bar, y bar, is my over m gives you the x coordinate, and then x over m gives you the y coordinate. That's always confusing, put y here and x here, but that's what we do. There's a moment about the y-axis for the x direction, a moment about the x-axis for the y direction. Comes out to be 0, 1/3. That's where you can balance the triangle right there. There's a draw it over there, but then people online can't see. If you take this triangle that goes out to 1 here and back to -1 and up to 1 here, it's a 2 by 1, 2 wide, 1 high rectangle. It balances right here, 1/3 of the way up, and 0, and the x-axis right there is where it balances. So I think that's a nice illustration of all this. Let's go back here. Now, a little bit easier topic, centroid. The centroid of a lamina, region, a thin plate model is a plane region. Is the center of mass, the book will say center of gravity, when the density function delta is 1. Actually, it turns out if you put delta equals any constant, it gives you the same thing. So actually, all we've been computing all along is also the centroid, because we always chose delta to be a constant, which is what I don't like about this section. I think it's got to be simple, so I understand. In other words, in this case, when delta is a constant, then you can write this one, that x bar is my over m, right? Is the integral from a to b of f of x, f of x, delta dx, over integral from a to b of f of x, delta dx. Remember this formula? This was the top, this was the bottom. We called this one my, we called this one the mass m. But if delta is a constant, guess what? We can pull delta out of each integral and cancel them, right? I can just take delta out front here and delta out front here. I used to write it that way. Cancel those. And here's the formula for any constant delta. And it's the same if we put delta equals 1, we'll get the same formula. If we put delta equals 2, it doesn't matter. This will be called the centroid. However, what is the integral on the bottom now? If I just integrate f of x dx. Instead of being the mass, it is the area, right? So if I cancel the deltas, this one reduces to x bar equals the integral from a to b x f of x dx. leave delta out because you took it out, cancel it over the area of the lamina. And then y bar similarly, you can cancel delta for y bar. Similarly, delta equals constant, including the case delta equals 1. Delta equals 1 in the other formula for mx gives, with the deltas canceling, y bar equals 1/2 integral f of x squared. The deltas canceled out. You just take delta out of there. You put it equal to 1 divided by the area, because the bottom is the same integral on both of these. So those are the coordinates of the centroid. And you want to memorize these, and it's easy because you just take delta out, treat it like it's 1, right? That's the definition. I think if I have time for my last little bit of stuff here, I'd like to finish this section. But the centroid has a real important use. There's a neat theorem going all the way back to an ancient Greek named Pappus. Who would think a calculus result would go back to him? Well, we generalized it a little bit since then. And it says this: the volume of the solid generated by revolving a plane region are I don't want to call it R. Let's call it D. Plane region D. About, or in a circle, of radius little r, let's say, such that the plane region does not overlap through the radius of the circle. So I'll say just without overlapping in the rotation. Is volume equals 2 pi r times the area of the centroid. I didn't write this right. Not radius, not of radius r. Geez, I don't want to do that. This is saying in a circle without overlapping. Is this, is where r equals the radius of the circle followed by the centroid. So the radius traveled of the circle, the centroid travels, and A is the area of the plane region, area of D. That's it. And actually, we've broadened this. Actually, even if it doesn't travel in a circle, as long as you can just take the area of the plane region times the distance traveled by the centroid in general. This 2 pi r is the distance the centroid travels in a circle, right? 2 pi r is the circumference of the circle it travels. And you can generalize this, say, even if it's not a circle, it's distance traveled by the centroid times the area of the plane region. So this is the theorem of Papu's for circles, but it applies more generally. That's a really neat result for something like you got a garden hose, you lay it around. What's the volume of the garden hose? It's just the area of the cross section by times the length of the centroid through the hose, right? So that's the idea. The length the centroid travels on those. So we can do this very nicely. A good time to do it is on the way home here. Erase this, I guess, to keep it on the screen. Homer Simpson's favorite problem, right? Find the volume of the donut. You know, called a torus in mathematics. Formed by a circle of radius 4 rotating with its center about the y-axis. At radius 6. This needs a picture, and that's obvious. Here's x and y, right? And you go out to 6 on the x-axis, and you take a circle of radius 4, so it goes back to 2 and out to 10. Here's my big old circle, right? And I take this and so the center of the circle rotates around to -6 and back. And as the circle rotates around, it creates a big donut that we call a torus. And sometimes we draw it like this. Anyway, so it makes a donut, right? You take the circular cross section here and revolve it around, you get a donut. What's the volume of the donut? How about that? I like this illustration because it's memorable. All right? So the volume we get by the theorem of Papu's is 2 pi radius traveled by the centroid. It must be getting late. Times area of the circle that's going around. Well, where's the centroid of what is the radius traveled by the centroid? For a circle, the centroid is right in the middle, right? The centroid is the balancing point using constant density, so it's right in the middle of the circle, right? But we're using the centroid. So the centroid is at 6 here, and the point at 6 travels a circle of radius 6. So this is 2 pi. Centroid travels a radius of 6. And the area is what? Well, it's pi r squared, for the radius of the circle is 4. So evidently we get 16 times 6 is 96, times 2 is 192 pi squared. There we go. So there's the volume of the torus. You just take the distance the center of the circle travels that you sweep it out with, 2 pi r, and multiply it by the area of the circle, and you get the volume of the donut. All right. So we'll stop that there, and I'll try these homeworks because we're out of time. And probably early next week, I'll put up some practice problems for the test because we're going to finish it at the end of this chapter, which we might have finished today, but if not, we'll finish next time. I can't remember. I'll let shuffle. I hit my homework. There it is. 5.7. Look at 1, 5, 7, 11. 5, 7, 11 to 17 odd. We'll skip 19 and then look from 21, 23, and 38. 38 is the theorem of Hopper's. All right. Fun stuff. You use it for physics. See you guys. Thank you online for coming in.